Hi everybody, this is the Chapter 2, Section 1 set of notes for Calculus AB. So our Chapter 2, since we're starting it today, you might want to know there's 4 sections to it. We do plan to go through all 4 sections and test at the end. So first section, rates of change and limits. First off is you need to know what a limit is. And the simplest way I can say it is it's the y-coordinate that you're approaching when x is approaching a given value. So what I have here, it probably sounds better. It says when asked for the limit of a function, you're asked what the height of the function is tending toward. And I did put in here that we don't actually care about the exact height at that x value. We just care about what the height is tending toward. So to kind of clarify that, I put in a piecewise defined function. Here's the picture of this piecewise defined function. So as long as x is not equal to 1, the function is going to be the line y equals x plus 1. So here's my line. Now when x actually does equal 1, then it's said to have a height of 0. That's the bottom piece here. Okay, so what we have is a line with an open circle where that point is filled in down below on the x-axis. So the question is, what is the limit as x approaches 1? So again, a limit is just the height that the function approaches. So as x is traveling along this line, getting closer and closer to x being 1, the height that the function is approaching is a height of 2. And it doesn't matter whether you're traveling along the line from the right side, getting closer and closer to 1, or traveling on the left side, getting closer and closer to 1. Either way, the height that the function is approaching is 2. Now, just because it's an open circle and doesn't actually exist to be a height of 2 doesn't matter. It doesn't affect the limit. So the limit is still equal to 2, even though there's an open circle there. Whether or not this point is given, filled in somewhere else, or just not given at all, doesn't matter. The limit as you approach 1 is 2. Okay, so here's a constant function, meaning your function equals just some number. So it happens to be 1, so here's my horizontal line at a height of 1. That's my equation. What is the limit of the function as x approaches 2? Well, no matter what x is approaching, the height is 1. So the answer has to be the height is 1. It doesn't matter if I said what's the limit as x approaches 7, or what's the limit as x approaches 12, or negative 4, or whatever. It's always going to be a height of 1 because it's a horizontal line at a height of 1. Okay, left and right hand limits. So some more notation here. When you, let's see, when you're looking at limit f of x, it's asking you for the height that the function is approaching as x approaches this number c. Well, when you have a superscript after the c value, which is either a minus sign or a plus sign, that minus and plus, those are indicating direction, either from the left side or from the right side. The minus is from the left, the plus is from the right side. So for example, when I'm looking at this picture of a piecewise defined function, if I'm asking you, let's say this is the final question here, what is the limit of my function when x approaches 2? The only way I can come up with an answer for that is if I look just to the left of 2, figure out what the height is approaching, which in this case is a height of 1. And if I look to the right of x being 2, getting closer and closer to x being 2, but from the right side, the height is approaching 3. The only way the limit as x approaches 2 with no superscript can exist is if the left side and the right side are approaching the same height. So this picture that we have here, definitely limit does not exist, because on the left side we're getting a height of 1, on the right side we're getting a height of 3. They are not equal. This equal sign right here is failing, therefore we don't have a limit. Okay. So if you're not looking at it graphically, if you're just trying to figure out from an equation what is the limit as x goes to whatever, most of us, first thing we're going to do is, well, if you want to know what y is when x is tending toward 3, won't I just plug 3 in for x and see what y is? So yeah, that would be the best thing to do, is just plug that number in and see what happens. So if you plug that c value in to your equation, your function, and you just happen to get a number, that's the y value. Congratulations, you found the limit. If you plug that c number in, and when you simplify your function, it turns out to give you a fraction with 0 on the top and on the bottom, well, that can't be our answer. 0 over 0 is an indeterminate form, so we're not done yet. So the key there is that there's some common factor on the top and bottom that we need to cancel out, and then we would need to re-evaluate it. So again, if you plug in your number for the limit as x, like for example, limit as x approaches 0, you plug in 0 for all the x's in the problem, and it turns out 0 on the top, 0 on the bottom. Again, what you're supposed to do is factor the top, factor the bottom, cancel out that common factor that you're going to see appearing, and then plug your value back in, re-evaluate it, and it should turn out just to be a number. Okay, third case, let's say you plug the number in and it's 0 on top, but there's just some number on the bottom, like 7 or whatever it turned out to be. Well, 0 divided by some number is still 0, so that one, no problem. So out of our 3 cases, basically you're always just plugging the number in, and either you get a number or you get, or you get 0, or the tricky one, if you get 0 over 0, you have to factor out the top and bottom. You'll notice there's some factor in common, like x minus 2 is on top and on bottom. Cancel it out, and then reevaluate it. Okay, so having said that, that's kind of our process that we're going through, algebraically solving limits. There is a special theorem here that you need to be aware of, and that is specifically for the function sine x divided by x. So this is kind of one of those problems where most likely on the AP exam multiple choice section you're going to see one problem involving this theorem. They are putting it on there specifically to see if you learn this theorem. So sine x over x, if you don't know what it looks like, you can check in the book or grab your graphing calculator, type it in, and see what it looks like. And what you'll notice is as x approaches 0, it's approaching a height of 1. So on the picture on the calculator, you should be able to see, on the y-axis, a height of 1 there for your function. However, graphing calculators are really not able to show open circles that graphs have. And actually, if we think about it algebraically, we plug 0 in for x. Sine of 0 is 0. And plugging in x on the bottom gives me another 0. So this is a case of 0 over 0, and I can't really factor and cancel. I'd be stuck because there's nothing here to factor. So it's turning out to be 0 over 0, but it's this special case of sine x over x. And so I have to pretty much just know that even though there's an open circle, which my calculator doesn't show me, but there's an open circle at the coordinates 0, 1, I know that the limit is still, as x approaches 0, the limit is still going to be 1. It's actually an open circle right there, but that doesn't matter for limits, right? It's still got a limit of 1. Okay, let's try a couple more examples. So here's a function, parabola on top or quadratic on top, linear on the bottom. So find the limit as x goes to 1. Okay, so first thing you always do, you plug 1 in for x just to see if you get lucky. Maybe it's just going to come out some number and you're done. So in this case, not so lucky, it came out 0 over 0. Again, when you see 0 over 0, you factor the top and bottom. You will see a common factor on the top and bottom. Guaranteed, you will see a common factor. Okay, otherwise you wouldn't be getting 0 and 0. Cancel out that common factor. Okay, which leaves me with just the function x plus 2, and I go ahead and try plugging in 1 again this time. So 1 plus 2, I get 3. 3 is my answer. So by the way, this rational equation here, this quadratic over linear guy here, if I were to graph that, its picture is a line, y equals x plus 2. Only thing is, there's going to be an open circle at the point 1, 3. So again, this kind of complicated looking problem here, when I go to graph it, it actually is just the line y equals x plus 2, only it's going to have an open circle when x is 1 and y is 3. Okay, the next example here, looking at 4 sine x over 5x, the question is, find the limit as x goes to 0. So again, as I plug in 0 right away, I'm getting 4 times 0 over 5 times 0. So 0 over 0 again. Again, I can't factor anything on this one. Hopefully you see the sine x over x and are thinking of the theorem. So by the way, the theorem has to be x approaching 0. It can't work for x approaching 1 or 6 or whatever. It's always x approaching 0. So what do? This 4/5, I just leave it out in front, and instead I'm thinking, okay, I'll split it up into 2 parts. So here I can take 4/5 times sine x over x. That's the limit of 4/5 times the limit of sine x over x. You can split it up like that. This is a constant function, 4/5, so I know the limit as x approaches anything of 4/5 is just 4/5. It's a constant function, like the other example. And then this part over here, this is exactly my theorem, and I know that this is equal to 1 by the theorem, and so my answer is 4/5. those can get kind of tricky. What they like to do on these problems is plug in like 4 sine 4x over 5x. And you want a 4x over a 4x, so you end up having to multiply by 4 over 4, so it looks like sine 4x over 4x. If that didn't make sense, don't worry, we'll see some examples of it, and I'm sure you'll get a chance to ask as you come to it in class. Okay, so for this one, notice the function x over absolute value of x. This is a very common function that they like to use. So this is a function that has a height of 1 off to the right of the y-axis and a height of -1 off to the left of the y-axis. And of course, when I plug in 0 itself, 0 over 0, again, you're supposed to factor and cancel, but you've got these weird absolute values. So it might be easier just to think right away in terms of the picture, where you have a horizontal line at a height of 1 on the right side of the graph and a horizontal line at a height of -1 on the left side of the y-axis. And so if I think, okay, the only way that the limit will exist is if when I approach it from the left and from the right, I get the same height. So as I'm approaching 0 from the left, I know that I'm at a height of -1. It might be quicker just to go straight to the answer there. I think on the left side it goes to 1. I'm thinking graphically. On the right side, I'm at a height of +1. The left side and right side are not equal, therefore, final answer, the limit does not exist. Okay, the algebra that I put in here, I'm thinking if I have some number to the left of 0, that means it's a negative number. So on top, my x value is a negative number. On bottom, because of the absolute values, I need to switch it to being positive. So the negative of some negative number would be positive. And so now my x's can cancel. I'm left with 1 over -1, which gives me the -1. On the right side of 0, well, I can take these absolute values off because they don't do anything if I'm to the right of 0 anyway. X over x is just 1. So that's the algebraic way of doing it. I think the graphing is actually a little quicker. Okay, so there's a slide in here on the sandwich theorem, but actually I've decided to skip sandwich theorem. It is in the textbook, but I don't believe it's going to be on the AP exam. It's a method for trying to solve limit problems, but there's ways around having to do this method that I think are easier that we'll talk about. Okay, so that's the whole PowerPoint. I hope you guys learned something, and I will see you in class for practicing the problem sets. Thank you.